Hi, Bobby.
Hey, Marek.
Just figured I would be a little early in case Alex or Praneet showed up early.
Yeah, thank you.
No problem. Hey, how you doing?
Hello.
Hi, Alex. Thanks for joining. I think we're just gonna wait a little longer for more people to trickle in.
All right, sounds good.
Hey guys,
Hi, how's it going?
yeah, man. So Is it in this session where we're having the UCLA model discussion or the next meeting?
No, but we're having it now, and then there's a little bit more time in the
Okay.
business group if we want to talk about some details and yeah, with like outside of the main meeting.
Oh, okay. Oh, I see. Punita. Okay. I invited a few other people from NXP because I thought this would be very interesting for them. If that's
Okay.
all right.
Yeah, of course.
Hey, Mark.
Hi, Puneet.
Yeah, Alex is also in, so I think whenever
Yes.
you guys are ready to start.
Okay, sounds good. What do you think, Bobby? Should we give it a few more minutes, or when do you want to start?
Well, let's do 8:05
Okay.
or 11:05, depending on.
Yep.
Hey,
I'm
Bobby.
kind of shocked that we got a grad student to wake up at 8 a.m., but such is life.
Hey, Bobby.
Hey, Puneet, how are you?
I guess I'll be seeing you again at UCLA in a few weeks.
Yes,
That'll be
I
great.
think.
Okay.
Maybe you do want to get started at testing your screen sharing. It should work, but Alex, or I'm
All
assuming
right,
we're
I'll
going to use
test.
Alex's screen.
Yeah, I'll test 1 second.
It's always sunny in LA. All right,
All right.
all
Yep.
works. Thank you.
You can see that. Perfect. All right. I think it's 11:05 and on the East Coast, so I think we can get started. So thanks, Puneet and Alex, for agreeing to give a talk today on 2.5D and 3D cost modeling. I'd come across your paper in July and thought that was very interesting, and it's great that you're able to share that work, and I understand maybe even some updates today.
Yeah, there's several updates since then.
Okay,
So yeah.
awesome.
Alright, yeah,
Okay,
so-
then take it away.
Yeah, thanks for having us. And I'll get started. So yeah, at any point here, if there's any questions, just feel free to interrupt and ask the questions where you have them. All right, so yes, we're working on a 2.5D and 3D cost modeling tool. General justification and need for this is, I guess there's a rise in interest in chiplets, kind of both in industry and academia. But in industry, we're seeing systems like the Ponte Vecchio, we're seeing AMD come out with some chiplets as well. And we're seeing several emerging startups that are kind of based on the idea of chiplets. For all of this, there's a lot of different trade-offs you get as you go from different kind of, I guess, design philosophies, from the monolithic design where you probably have best performance, you have lower assembly costs, things like that. But then when you possibly have some very bad yield, chiplets can improve the yield dramatically. And there are a number of other parameters which get helped by splitting the chiplet. So questions we have here is kind of, where do we draw this trade-off? Where's the best kind of sweet spot for our designs? So what we really need for this is we need a modeling or a cost modeling system which can take kind of any number of these different kind of design parameters and give us some idea of which will be the best for our application. And I guess what would be cost optimal, ideally also things about performance. But for what we're focusing on cost. And this could be integrated with other systems as well to kind of find a optimal point for your design. So basically what we do is we we have a model that takes kind of a wide range of
Mhm.
factors. We want to take things like testing,
Hey,
assembly.
sorry,
So
Alex, excuse me for a minute. If you're not speaking, would you mind going on mute, please? We have a bad bridge.
Thanks.
All right, thanks. Okay, so I'll get back into it. This basically, we need some tool that can cover a wide range of factors and model all these different options, whether it's monolithic to 2.5D or 3D stacking for our designs. And our design, which we worked on, covers a wide range of these factors. So basically, this is a kind of system overview. On the left, we have the kind of input files. We have a system description. We have assembly technologies. We have IO cell definitions, layers, definitions, wafer processes, test processes, all of which we take as input files. And we have a fully parameterized model, which based on those input files, basically constructs a design and computes an estimated cost based on those input parameters. So I'll kind of go into a bit of a kind of description of how the model works and kind of some of the use details on the next few slides. So starting off the system definition. So this is a structure which is kind of hierarchical and fully parameterized. So it should be very easy to change configurations, and it should be very flexible to what configurations you can model. The kind of core of this system definition model is a chip object. So basically a chip object is, well, in the figure on the right here, there are 4 chip objects. That is, there's a memory, CPU, GPU, and then also an interposer or integration substrate chip as well. And each chip contains its own power, voltage, and core area parameters, as well as some layer stackup, which contains information about what technology node is implemented in. And then each chip also references its own assembly methods, wafer process information, and testing processes. And the way this is structured, which will become clear on the next slide, is basically each chip also, in addition to its own self parameters, it contains a list of any chips which are stacked on top. So in this example, there's an interposer, which has a CPU and GPU stacked on top. And the CPU has a memory die stacked on top of it. So here's what the system definition file looks like. It is in an XML format. And I've, for the sake of space here, some of the parameters aren't showing in this code snippet. But basically, there's core area, there's power, operating voltage defined in each of the chip objects, as well as the name of some assembly layer, wafer process, test processes, which are defined in separate files. And also the netlist is defined separately. But what you can see here is the way that the kind of 2.5D or 3D stacking is defined is we have this interposer chip XML object, which is defined, which is kind of the, I don't know, the root level chip in this case. And then within that, there's 2 chip objects. There's the CPU and the GPU. And within the CPU object, there's also the memory object. And so based on this, this kind of allows the system to run a lot of functions kind of recursively through the chip stackup. And it should be extensible to any depth you want. Yes. Is there a question?
Yeah, we've got a bad bridge today for some reason. Apologies, everyone. If you wouldn't mind going on mute if you're not speaking.
Sorry, I didn't realize it was my fault.
All right, no problem. Yeah, if there's no questions, then I'll continue on here. So yeah, this is the system definition file. So this is kind of the physical chip stack. Next, what we need is we need some connectivity. And so for this, we have a netlist file definition, which is in a format like this, where basically each netlist entry defines a type of IO, and it also defines which blocks are connected and the bandwidth between those blocks. So this means that 2 blocks, for example, could have multiple connections between them of different IO type. And there's a lot of flexibility here. And yeah, right now the connections are all defined by bandwidth. We are intending to support both bandwidth and wire count definitions later on. As of right now, it's defined by bandwidth, which means you can go and say we need this bandwidth between these two chips, and we're planning to use this interconnect scheme, whether it's some parallel or serial method. And basically it should automatically select the necessary, I guess, number of channels you need, and the correct associated wire count from that. If you want to have external connections, this should be defined with kind of a dummy block definition, which would be an external block or maybe some other name that you choose. IOs they do have the option to be either bidirectional or unidirectional. So you'll see if you look closely on the image on the right here, basically the UCIe connections here are defined as bidirectional IOs in the IO file, so you only need to define them once. So basically CPU to memory, that defines both directions. If you have something like I guess a GPIO, which is just a single unidirectional connection, you would need to define that in both directions. So the IO definitions, which are referenced in this netlist file, so there's basically a variety of different IO types and different interconnect schemes here. Basically, the netlist file is used to build an adjacency matrix for each type of IO. So there's basically a list of these connectivity matrices, and each IO has basically has the definition here. And for this example, we can say if you have this UCIe standard cell definition and you have block 0 and block 1, if you need a link bandwidth of 1024 gigabit per second, you would need 2 of these connections. Since this bandwidth is a bidirectional IO, yeah, so that's what we get here. And this is used to add IO cell area to each of the blocks when we're computing costs, for example. Since now we have 2 IO or 2 UCIe standard blocks on each side. I'm hearing some noise again. Did someone unmute for a question or? All right. If not, then I'll continue. So pretty much we have a few different kind of ways that the area can be defined of a chip object in this system. So basically it'll pick whatever the maximum of these is. So the first is core area plus the area taken up by IO cell drivers, or IO cells, which include drivers, ESD, for example. The other, or the next possibility, is a chip could be defined by the size of the chip stacked on top. For example, in a 3D stack, if your top chip is larger than your bottom chip, you probably need to extend the area of your bottom chip to account for that. And in the case of something like an interposer, if you have 3 chips stacked on top of this other chip, the interposer, for example, may have no core area, and it'll be purely defined by the area of whatever dies are stacked on top. And then the final option here is that the chip object could be defined by the pad area of the IOs coming out of that chip, which includes both power and signal pads. One other consideration we use here for determining how much space is taken up by IOs is we look at the IO cell reach. So basically, reach determines where on the chip it is valid to place an IO cell. If you have, I guess, a IO with a reach of say 1 or 2 millimeters, and you have a chip which is 5 by 5 millimeters, you can't place that in the center of the chip because it can't drive far enough to get out of the chip. So basically, we do account for this reach computation as well. And if there's not enough boundary area that satisfies this chip or this IO reach condition, we increase the size of the chip to increase the perimeter and the perimeter area where these IO cells can be placed. So the next thing, this is kind of back to the chip definition. Each chip has its own list of layer objects. So in the simplest version, we can do this in terms of, I guess, you could have a single layer defined for a chip, which in the example on the right here, we call it combined 5 nanometer. And this basically is an approximation which includes all layers inside. But you can also have a larger number of layers to do some more fine-grained modeling, or kind of, you can also model the required number of metal layers or something, for example, using that. This kind of allows a bunch of different options. You can use the same chip object for PCBs, for interposers, any number of different tech nodes for chiplets. And yeah, so a little figure here, and basically it just shows how you can either have this option where you have multiple layers defined. Here we have a active silicon and then 6 different metal layers, or you could just do a combined layer which contains everything. And yeah, this is used basically for determining things like basically the cost and yield in terms of the area stack up and wafer parameters. And we use a negative binomial model for yield. And in the case of the multiple layers, we use that across each layer, and each layer could have its own, say, defect density and probability of probability of having defects, etc. Or we have a combined model as well. So there's a wafer process definition as well, which is included in the model.
Maybe one question on the previous slide. So it's interesting to me that you're giving the option of like kind of modeling the silicon either as just one item combined, or like breaking out the metal layers and the, I guess, yield of that. Are you doing that because you want to be able to model, say, that you need to add more layers to a chip in order to go to like use a certain interface? Or is this more for, say, the substrates and interposers where, again, the interface may dictate the number of metal layers?
Yes, so that was the initial reason for this. We wanted to, for example, on an interposer, if we switch between different types of, say, a parallel versus a serial interconnection option on, say, an organic interposer, maybe it doubles the number of metal layers required versus maybe a tighter pitch wire layer might not, or sorry, a tighter pitch option might not need as many additional metal layers. That was the original reason for this. The reason why, I guess, the numbers we could find were, for example, we could find full wafer cost published numbers for several different tech nodes, but we weren't able to find kind of realistic numbers for different metal layers and for active silicon. Kind of, we weren't able to find that breakdown. So yeah, I mean, we're still looking. If you guys know of any place that has that, or anywhere to get those numbers, that would be quite helpful for us. But for now, basically, it does support it. We just don't necessarily have the right numbers for the fine-grained version. And yes, we are planning to do, once we can find the numbers for a good study, we want to do that number of layer study as well.
So one more small thing to add to what Alex just said, this getting reliable numbers, especially for organic substrates, has been harder. I mean, right now we are kind of largely relying on assuming that the organic substrate costs kind of closely mimic organic PCB costs. And that would not be completely accurate, but those are the numbers which are easily or publicly available. But on organic interposers, the material and the fabrication and the per layer costs have been somewhat difficult to find, even more difficult than silicon. So, so if any of you can help us with that side, that will make just the default setup much more reliable in terms of numbers.
This is Trent from NXP, and the thing about these organic interposers and even the organic substrates and the silicon technologies, for that matter, is that the cost is dynamic, right? So do you think it might be beneficial to have it some type of maybe a user input for some of these parameters?
But they are all user input. It's for us it was more about creating at least a default setup that people can use giving out kind of reliable or reasonably reliable numbers. Absolutely everything is user input here.
Oh, okay, got it. Thanks.
Yeah. For example, basically the layer definition file, what it looks like is a list of any number of these layer objects, like shown in this image here. So basically you can just add as many as you want and then reference them in your design definition. So the idea is you define all the parameters for your layers, but at least for our study, we're doing our best to get good numbers. And we'd also like to have kind of on the template kind of initially available files for people. We'd like to have something reasonable in there. So it doesn't have to necessarily match every design you're going to do. Because I know at least in organic, there's how many different, we say organic, but there's so many different options of what that actually means, like what material it actually is made of. And yeah, a lot of different processes as well. So yeah, we're kind of looking for reliable numbers on one of those at the start.
Got it. Thanks.
All right, so moving on from this, the next thing is we have a wafer process definition. So basically this kind of collects a bunch of parameters that would otherwise kind of have to be repeated in several places across the design. So this is things like we have edge exclusion, we have the dicing distance, which are the basically space you need between dies. So basically this determines how much of the wafer area can't be used for chips. So this doesn't account for, I guess, how well the chips fit into the wafer, but that'll be on the next slide. This also includes things like reticle dimensions here. So to determine, I guess, the utilization of the reticle based on the die fit, we do effectively this. So we basically try a couple different ways to fit for a single die size, which we're trying to evaluate the cost of that die. We try a couple different options here. So to try and fit as many dies as possible. We take the maximum of these two. This gives us a count of the number of dies that fit, and then we take that as our utilization of the wafer. And I guess the reason we're doing it this way is because typically the cost numbers we were able to find were basically cost for a full processed wafer. So this determines how many dies we get out of that. So
maybe just to comment on the picture that you're showing here, this is like an interesting idea. I haven't really seen anyone kind of like having like shifting things around to fit more die on a wafer. And like one of the constraints would be like that you have to like dice this, and if like in this case they all line up in terms of their rows, but they don't line up in terms of the when you want to cut the columns. So I'm not sure how like realistic this would be. Like I'm sure there may be a way of how you can handle this, but I think in the end you'll probably still end up using some kind of like grid version of a die layout.
Okay.
At least that's my opinion.
All right, that's a good comment. So you're saying that in general you would expect it to have to be a grid, not like this. Okay.
Yeah, exactly. Just for like the singulation aspect alone. And I'm sure there are like, even if you think about like how these things are indexed, and like basically you need to know where the die are on the wafer. Usually that's done with kind of having coordinates and just stepping through how many, like basically the number of rows and columns. And then in that case, it gets confusing if they're not on a grid, basically.
Okay. Perhaps
so,
that's something
Marek,
that would be good to add as a flag.
Quick question.
Yeah.
Is that true even for these newer dicing techniques, like these plasma-based dicing techniques?
I'm like, I guess I can only comment from what I've seen like being used at least at ADI in production. I'm not sure if like if people like extract a little, like a couple more die using something like this. And I think it's technically possible, but the question is how easily does it work with kind of the established systems that people rely on.
Okay, great.
Like maybe somebody else can comment here on the call.
I believe there was a paper which we saw, trying to remember, a while back, which was was trying to get the idea of whether or not a hexagonal chiplet makes sense. And I guess the problem, of course, is the dicing. So they were claiming it could be done, but it was just not, yeah, it was just not good with our kind of current dicing methods in general. So I imagine this would at least be better than kind of an oddly shaped chiplet.
So I think Alex, but that's a good comment. I think we should at least let the default be a pure, completely gridded structure.
Yeah, we can make a default and maybe find a way to add a flag somewhere.
Yeah.
Since this is, I could put that into the wafer process definition and basically say gridded or flexible.
Okay.
So, okay.
Yeah, that sounds good. Thanks.
For the comment. All right. So another factor here which affects silicon cost is the reticle size. So if you have very large chips which are larger than the reticle size, you might need stitching, and this affects yield. The other possible factor here is that the size of your chip determines how well it fits into the reticle, and how well the chip fits into the reticle can determine how many exposures are required to fill an entire wafer. And since I guess lithography machines are very expensive, this can actually be a pretty large percentage of cost for advanced nodes. So a number which we saw was, I think, around 30% of costs go to lithography in 5 nanometer. So this can have a noticeable impact as well on cost. So we model this as well. So next is the assembly process definition. So this basically, for each assembly process type, we define a bunch of parameters here shown on the right. And the general idea here is we say the cost of assembly is largely dependent on the machine cost and the time spent on those machines. So we have basically defined both a cost for a pick and place and a bonding machine. If they're the same machine, then you can just set the costs the same and everything will work out. Yeah, so basically some kind of intuition about this. Basically, your total assembly time is going to depend on how many dies are placed and bonded simultaneously. If you're using something like thermal compression, copper to copper pillar bonding, assembly time is going to scale, or if you're doing individual placement, the assembly time is going to scale with the number of dies. So this will be your placement and your bonding time for each die times the number of dies. If you're doing something like solder reflow, basically you would typically be placing all your dies and then bonding once. So this will scale noticeably better since only the placement time is scaling. And again, it is possible that you could be placing multiple dies at once. And this is accounted for in our definition here, where instead of defining as either simultaneous or individual, we defined as bonding group size. So you could either have a very large bonding group of number of dies which are, I guess, placed or bonded at the same time, or you could have down to 1. And if we're doing something like hybrid bonding, that is probably closer to the reflow case, since you basically do a dielectric bond individually when the dies are placed, and then you have a, I guess, heating or annealing step. So next is the yield. So to get the assembly yield, we use this equation here. So we say the first term here is the alignment yield. So this is some yield factor which is determined by the number of dies which are being placed and the possibility of one of those going wrong, I guess. The next is the probability of a single bond of one pin failing due to some defect, and this scales with the number of pins. And the third term here was added for hybrid bonding specifically. And in the case of some of the others, we might pick a defect density which zeroes out this term or sets it to 1. But basically for hybrid bonding, since there's a initial dielectric bond step where it is possible if there's a defect or an impurity that can prevent making a proper dielectric bond before the heating step. And that is another mode of failure. And since that is an area-based factor, we also use the negative binomial yield model here to determine the probability of having one of these defects. So as far as modeling integration substrate types, with the layer definition, which I described earlier,
Yeah,
we
Alex?
can basically, yes.
So in the previous one, especially with the hybrid bonding,
Yeah.
A single misalignment can take out a number of pins, right?
Yes, so a single misalignment, that failure, we'd just consider that a complete failure. So that would be an alignment issue. The pin yield would be more of a properly aligned die, but there is some defect or some void in the copper, for example.
I see. So your alignment yield is different from your assembly yield.
So the assembly yield is the cumulative of this alignment and bonding and hybrid bonding.
Oh, I see. So you're basically accounting for misalignment in terms of just simply saying in the first term.
Like pick and place.
Right. Okay.
If it's off or
Yeah,
angled or the die gets moved, that would be the
so,
alignment. Yeah.
Yes, Bobby, just to confirm, the alignment yield is on a per die or per chiplet basis. The bonding yields are computed for a chiplet using the number of bonds that you have to bond.
Yeah. So Srijit had some like interesting information on this. He used to be at Intel, now he's at Ampere. Yeah, Srijit Chakravarti. So yeah, I don't know whether he's published numbers, but he's sort of cooked up estimates for these things.
But that again, that would be great to know if these are anywhere to get hold of them. That would be absolutely great to know, because these are equally hard to come by publicly.
Yeah, I don't think. Well, I think he's given more fault models that you sort of work backwards from. But he's the only one I've seen who sort of published something about this.
So this model itself, we had done a little bit of work along with IMEC to kind of make sense of the simple assembly yield model, and that's where Alex had come up with this final model, including for the hybrid bonding case.
Yeah, makes a lot of sense. Thank you.
Yeah. Additionally, if anyone else has insight on the hybrid bonding model yield here, we discussed this with IMEC, and basically we decided that there needed to be some area dependent term. But yes, this is if there's additional insight on this, we'd appreciate it as well.
No, there's a density dependent term. I don't know whether that's you sort of cooked that up directly. Sorry?
Defect density, you're saying, or
no, the pin density. So the denser the pins are, the greater the likelihood.
Yeah. So I think that is not yet modeled. There is a copper density dependent term as well, because that increases the likelihood of dielectric bonding failures.
So that is or you're saying for the hybrid, okay, sure, I see what you're saying.
Yeah. So I think that term is not yet there here. I think at least for now, we have been assuming that would be kind of in some sense design ruled out.
Well, also I think if you're basically going to be defining some assembly type in your assembly definition, and that will give you, and you'll define there your defect density. So that number could change depending on, I guess, your copper density.
No, I think Alex, right? The right way to do it is that if it is a big issue, the copper density dependent failures, then it should just be another yield loss term.
Okay.
And Bapi, if you know if Srijit has published that or put it in some sort of even a blog post somewhere, please let us know.
Yeah, he's the closest. I'll send you the deck he sent out, but he's the closest I've seen in public.
Yeah. If you can send anything that will help us refine this model, that'll be very helpful.
Maybe two other comments on this. Like, first of all, I think it's great to see kind of a little bit more like thinking about like what the underlying mechanisms are to then get to the yield. Two things that you may want to account for one way or another is the effect of having redundancy built into some of the chiplets themselves. So if you take UCIe, for example, and you have spare lanes, then it may look artificially bad here in your assembly yield when actually a couple of pin defects would have been handled fine by the interface. And then so this is one direction. The other is that kind of from an industry standpoint, this is certainly like the correct way about going about the assembly. However, you may come from the other side and say you're using empirical data from previous products. So you may not know like all of these terms, but you know that a package of this size with this many like bumps and this many chiplets roughly in the end comes out with this yield. So that like when you have these files, that there's also an option to say, I'm gonna like basically like skip over all of this like actual math and just going to put in the value that I think is roughly correct for the assembly process I have.
Yeah, that is something definitely which is on our short list of things to add, which is basically kind of a black box definition support. So basically that would be things like what you're saying. We basically bypass these parameters and basically just give definitions of things that are typically computed. So yes, that is definitely on the short list, and that's a very good point. All right. So then, if that's it for here. So yeah, again, anything you guys have that you could send us would be very helpful, and we'll work on adding that in. So next here though is the integration substrate type. So this was kind of mentioned earlier with talking about the layer definition, but I wanted to kind of reiterate here. We can model different types of substrates. So we can do organic, which we're basically generally assuming it is extremely cheap, has no reticle concept, so there's no reticle stitching yield impact, generally has wider bonding pitch. And then something like silicon or glass is more expensive, reticle based, and probably has much finer pitch bonding available. And in addition to this, we added some flags to support EMIB. So basically EMIB, the idea we can use some sort of organic, for example, substrate, and we embed these bridge die to take advantage of kind of the very fine pitch interconnect which we can get with silicon, but we could have very large interposers here without running into reticle stitching, for example. And if we want to implement this in our design, there's basically a flag to mark dies as buried dies. You'd basically just add an extra bridge die to your chip definition, and you'd mark it as a buried die. So it would basically not take up any space on the top of the integration substrate, and then you just would add it to your net list as well. So the next thing which we're working on is test modeling. So this is something which is currently in progress, is collaboration with the student Janti Talukdar from Duke. And yeah, this is partially implemented right now, and the full version should be available within the next week or two. The current version that is available, which you guys can download and try right now, which I'll have that on a later slide, but that does not have this test modeling yet. But it will be in there very, very soon. So the way we're doing this test definition and test modeling, so we're trying to get both yield impacts of kind of how effective test is, along with the approximate cost of the different tests we want to run. So basically, this is also defined in XML library format, so you can have any number of different test processes, and each chip object is given a test process, which it selects from that library. And the way we are structuring this is the test process has a self-test. So this means for the chip itself, is the chip tested before it is integrated with the rest of the system? And then also an assembly test, which means for that chip and any dies which are stacked on top of it, how is that tested as well? And basically we have a few different parameters here. We have things like defect coverage, cost per area of testing, and pattern count, so the number of tests which we're trying to run. Yeah, and again, this is very close, but still pending in the current release. I'd hoped we'd have it, but we still probably need at least another week on this before it'll be released. So next is kind of how this fits into yield modeling. So we have some concepts here. There's true yield, which is basically with our negative binomial yield model, we get some actual yield of the chip. But this isn't necessarily, all those defects aren't necessarily caught when we do testing. So there's a tested yield as well, which will be higher than the true yield, most likely. And then we will also have a concept of quality, which is the number of tested passed dies, which are actually good. And we basically, through the stack, as we build this up from the system definition file, we compute these parameters and they kind of ripple down. So here's here's a relatively sprawling block diagram, which is about to show up. But basically, here's the general flow for how this would work for this system. So effectively, we can get some cost and true yield directly from the memory die. And then based on our testing parameters defined for this chip, we get some quality and some tested yield. And this then gives us basically our cost and quality for this block itself. Next, if we're going to stack this on the CPU, we do the same thing for the CPU die. So it can do its own self-test and get its own tested cost and quality. And then we combine, and this would be kind of the assembly testing parameters showing up here. So we account for both the qualities into the new yield of this stack. And then we also can account for cost here. And then we also do tests after this stack is assembled.
So just to, just to illustrate why we are going through all this kind of weird complexity is mainly to account for the fact that known good die is going to be very, very difficult to engineer in context of these chiplet-based systems. So most die are likely to be sort of probably good die, and this whole business of test quality, etc., is trying to address that.
Yes, that's true. And the other thing which we wanted to mention is that, for example, if we had a monolithic design and say we fully exhaustively test the die, that will cost a certain amount. And then if you consider you split that into chiplets, and if you want to test each die individually completely, but you also want to test at every step of the assembly, it is entirely possible that testing cost is going to multiply by a factor, a relatively large factor. So we also, we wanted to make sure that we have basically the options built in to do, I guess, incomplete tests for the sake of, I guess, saving costs. If you have a die, like, for example, maybe you don't care so much about the memory and the CPU here, but the GPU is very expensive. So maybe you don't test the memory and the CPU individually, but you test them as a stack before you integrate them with the GPU. So those kind of things are options with this test modeling. And then, just to finish up the system here. So basically, after this, we have the cost of the stack after testing. And we do the same for the interposer. We do the same for the GPU. And then we integrate that all. And then we will have a final system tested, quality and yield as well. All right, so next, this is most of the kind of functionality description slides here. So next I'll go into test case and some results. So we look at this kind of generic graph processor test case. So if we say start with an 800 millimeter squared SoC, so this is similar to what I had in my paper for those of you who have read it, with some modifications. But basically, we take a large graph-based processor and a grid layout, which we assume is a square of cores, and we can split this into a number of chiplets. So basically, here we could go from this 800 millimeter squared monolithic chip to a 4-chiplet version, or say a 16-chiplet version. And in this case, there's a few things to notice. So first off, if this were, for example, if there are 64 nodes in the graph processor, the monolithic would contain all of the nodes or cores, and then each of the progressive versions here would contain a smaller number of cores. And since we're looking at it like this, note that basically, since we're considering the inter-core, inter-node bandwidth to remain constant, this means the bandwidth which is crossing a chiplet boundary increases as we increase the number of chiplets. And this reflects on the full design in terms of IO cells that are needed in the 3rd version here, but are not needed in the 1st version. Yeah, so using this model,
Wait,
we
sorry.
Yes.
Do you mean the number of IO cells or the type of IO cells?
Well, the type of IO cells would be different. I guess if there's the monolithic version here, and the 2 chiplet versions would probably use the same type of IO cells within, where they could conceivably use the same type of IO cells for the interchiplet connections, but the number will greatly increase of these interchiplets.
But then
hold on. Why
your
would it? But your cross-sectional bandwidth is the same, right? So,
I'm sorry, the cross-sectional bandwidth, yes, is the same. But
so
there
why
are
would that?
factors
Why
here.
would those? I mean, you need between the 4, right? You need 4 gigabits, and then with that same bandwidth, you know, is 2 lanes of 2 gigabits. So,
Yes.
so it should be just
So
I think the
here's
difference.
one thing here. So basically, one thing which we have is, if we split the monolithic design, the IO cells are required for a couple of reasons. We're increasing driving distance because of chip separation, and there may be some ESD protection required for the assembly process. But then the other thing to mention here with what you were saying, the 4 gigabit per second, which is being split into 2 gigabit per second, is true. But look, within that die, there's additional connections which didn't exist before between those 4 die. So there's an additional 4 connections of 2 gigabits per second each.
right because you've taken one of the quads and turned it into an octet.
Yeah. Yeah.
Now the ESD protection, though, I'm seeing that the you know, at least the industry is going down to like 5 volts, which are extremely. It's almost the parasitic. The parasitic
industry is scaling it down, and that is kind of, it's kind of almost being forced for these kind of, particularly these chiplet and 3D stacking options. If you don't go very low, it becomes extraordinarily unreasonable. Yeah, so at least as far as the results on the next slide here. So yes, you can pick whatever IO cell you're using or you want to use, but we're assuming likely there'll be some additional driver space, and likely there will be some ESD area which would not be taken up in the monolithic version. So
Yes,
that will
I think
still
just to reiterate what Alex is saying, I think the total number of signals going is all the same in all the designs from core to core, but the only difference is we're assuming that the IOs or signaling within the single chiplet, that's essentially 0 cost. But when you need to cross a chiplet boundary, that's what I think Alex is calling as a sort of IO cell.
Yeah, and we've looked at this. I mean, what I call the chiplet tax, right? Because now you have area on each one of those chiplets that's for the die-to-die connection that didn't exist in the monolithic. Right? So every chiplet gets the chiplet tax.
Absolutely, this is basically computing the chiplet tax. Yeah.
But wait, but coming back to this, one important thing: off-package IO will take far more area than intra-package IO for the same, right? So, but at least I didn't hear that accounting difference, maybe is the right way to put it.
That will not be affected in this design. So basically we have the same amount of off system or off chip IO. We have the same amount from the left to the right. So
but
in our system, we can define that as well. Using the external block, you define a specific external IO, and in the netlist, you include connections to this dummy external block. So that can be modeled, but that doesn't affect the, I guess, general scaling here, since that would be constant.
Yes, and okay. Anyway, but I think you're penalizing die-to-die IO more than you should, is my instinctive reaction based on what you've said.
Bobby is not. The smaller those die get, the tax gets bigger.
No, they're 2 different things. Is there a tax? Yes. I'm not, obviously there's a tax, yes. But the actual area cost of a die-to-die IO is significantly lower than the area cost of an off-package IO.
Yes, that is true.
Yeah,
So
definitely.
We do define different
per
IOs.
chiplet.
Yes.
But on a per chiplet basis, the smaller you make that chiplet, and especially if you're on an organic substrate, that tax gets to be pretty significant.
So Alex, I think the comment from Bapi is, I think, straightforward to address in a revised version of the study, just use the kind of relatively right-sized off-package I/O, the usual 1.8 or 2.4, 2.5 volt type IOs. That's from the standard IO library, and those will be much larger. And I think the conjecture is that the absolute difference or the absolute chiplet tax probably is not going to change, but the relative chiplet tax might reduce.
Yes.
Yeah.
Right.
Yeah.
Oh, actually, I was thinking the other way around. That the relative, the absolute numbers go down. But you will see a tax. But yeah, one of those two.
Yeah.
No, no. Believe me, I've been doing a lot of these what ifs. The chiplet tax gets more significant the smaller your chiplets get, especially in this array.
Yeah.
Yeah, so nobody's there's no debate on that. I think it's a question of what is the actual weight accounting cost you're giving to the die-to-die IO.
Well, it depends on whether it's a organic substrate or it's a advanced package.
Bingo, that's a discussion. That's exactly the discussion with Puneet and Alex.
Yeah, you'll see some results on our early estimates on that question. Again, with the caveat that our numbers, especially for organic, are less reliable.
So what I do on the next couple of slides is the types of IO cells which I use for these interchiplet connections. They're not using a full-sized GPIO cell. They're using a reduced size IO cell, which was designed by a previous student in our lab specifically for a chiplet die-to-die situation.
Yeah, but it's not, the driver is really not the main issue. It's the pad. It's the pads, right? It's the footprint.
Pads are counted as well, and that, I guess that's going to be an impact, which is kind of regardless of the size of the drivers, for example. Yes, you need very high density, and on organic, that's a very, very large penalty. So you'll see those in the results on the next couple of slides.
Let's get there.
Yep. All right. So here, first off, the organic versus silicon. We have so here basically you say organic, sure, cheap, no reticle stitching, but there's wide bonding pitch here. The silicon or glass is more expensive with some reticle stitching, but it has very fine pitch interconnect here. So in this plot, so this is for 4, 9, or 16 chiplets. So what you see basically is that the silicon with low bandwidth versus high bandwidth is actually relatively similar here. But with organic, when you go from lower to higher bandwidth, the cost jumps up pretty dramatically because, again, this is some combination of number of IO cells required, but also the number of pads, bonding pads required.
But Alex, here the signaling is completely parallel IO, right? In this study,
this is all parallel IO, so this does not use UCIe. So the next slide, I'll talk about the parallel versus UCIe. But yeah, this is all.
And is this? I'm sorry. Does this include the package cost?
This includes, this does not include packaging, but this does include assembly, and it includes assembly, yield, silicon, so all the costs which we described on the previous slide, but not once you have this assembled, say 2.5D system, it does not include packaging on top of that.
So the silicon or glass interposer is not built into these costs?
Sorry, what did you say?
The glass interposer or the silicon interposer is not reflected in these costs?
So that is actually reflected in the cost. Again, we're not sure about our organic cost, but basically we do have that defined as a chip. So basically this system here is effectively the interposer plus some number of dies stacked on top. So it is the cost of the, say, silicon in each, or in the case of the organic, the cost of the organic die, which are our best estimate numbers.
But you have to also add the cost of the organic interposer, because that silicon interposer has to sit on an organic, right? So there's also an organic substrate.
So what we're kind of assuming, so basically, I guess, you likely would have some kind of packaging, but if we're having the silicon, so in a design our lab taped out, what we did is we had a silicon interposer, and we basically placed that directly on a PCB and then wire bonded it. So I guess in that case, yes, the organic or the PCB is sort of an organic substrate,
Yeah, all right.
which we could theoretically, we could model that, but it's not modeled in here. We're basically drawing the line at the chip boundary.
Okay, because in all the packaging I've seen, there is an organic substrate under the silicon interposer, right? And that would then be added to the package cost of the.
Yeah, but Nick, the organic interposer and that the packaging organic substrate, I mean, they still may not be the same. Because
depends on what you got to fan out to the outside world, right?
Because the final organic substrate or the laminate or the organic interposer, what you're calling as interposer, is just used for kind of package level fan out. And if the interposer is built well and the system is designed well, that would be kind of simple.
But if you have to go off to, let's say, 4 banks of DDR, whether they're on a glass interposer or their organic substrate, still has to carry all those signals.
Yes, but what I'm absolutely. But what I'm saying is that what I'm not sure is, in case of an organic interposer, will there be sort of a different organic substrate below the organic interposer in addition as well?
Right.
Or it's one monolithic organic substrate with lots of RDL layers in it.
Hey, Puneet.
Yeah.
Excuse me for 1 second. We've hit 9 o'clock. But if there's nobody has any objections, we'll just keep going into the bleeding into the business meeting. Marek, I'm assuming that's okay with you as well, right?
Yeah, no, that's perfectly fine.
Okay.
Yeah. So I have only 2 more slides.
No, you can take all the time you want. We're
If
just going to
anyone
roll
needs
in.
to leave now, I could jump to the slide where it has the information for how to actually get to the cost model. But if everyone can stay, I'll be there in like 2 minutes probably.
So Alex, what's the cost value here? Is that like dollar? And then what's your like SPW there, like 1,000, 5,000?
Okay, so yeah, so that bandwidth is gigabit per second as the external bandwidth here. So in this case here, this is 32 gigabit per second in what I drew out here. So this would be 1,000 gigabit per second or 5,000 gigabit per second as external bandwidth. So the internal bandwidth again scales with the internal inter-chiplet bandwidth scales based on how many dies. But that is the external boundary bandwidth.
Got it. So what's your cost unit here?
Cost unit here is an I guess US dollars, which I should have marked.
Okay.
Yes.
Thanks.
Right. Yep. Okay. So this is for the organic versus silicon, and I have the same thing here for parallel versus serial I/O. So effectively, the triangle marked lines here are the parallel, which is the same as what was on the previous slide. And then we have UCIe advanced for the standard for advanced substrate, and then we have the UCIe standard, which is defined more for an organic substrate. And I guess to note here, I'm doing all the lower bandwidth. So on the past slide, I had both the 1,000 gigabit per second boundary and 5,000. This is just 1,000 here. So what we see here is kind of more what you would expect to see. We have basically the in this case we see for the we see basically organic is cheaper than the silicon in the low bandwidth case. This does actually change a bit when we go to higher bandwidth, but in this plot here you just see the organic is cheaper at lower bandwidth, and you see the way it scales kind of at least at this lower bandwidth, actually the parallel is better. And then also to notice is when back here we already saw how the organic scales very badly at the higher bandwidth. But yeah, this is some general idea of what's going on here. And what I'd also like to say, we can answer lots of questions as well. But since we're kind of at the end of the first meeting, here's the current release of the model. So this has everything which we talked about, although the testing cost is not fully implemented as the caveat. So this would be available for you to start trying out if you like. right.
Those
And
of
yeah,
you who went through the DAC paper that we had, one
Puneet,
of our
just for kind of this first half here, I think that was really interesting, and I guess can you give like maybe for everyone a little bit more insight into how you would actually like once you follow that link, like what do you see, like how do you actually use that that model?
yeah. So let me see if I don't think I'm fully sharing my screen. You guys can't see. So I just clicked on the link. You guys are still seeing the PowerPoint, right?
Yeah.
Yes.
Okay, so let me see if this works.
Hey, Viswa.
Yes, we can see it.
Okay, great. So basically here, so
Hello,
this
can you hear
is,
me?
yes, I can hear you.
Mute problem.
Is that a mute
Yes, now.
problem?
Hey, Nick, you're not on mute.
How you doing? How you doing?
Okay, we're gonna.
Okay. All right. So
Oh,
what you
that's right.
see,
I'm sorry, I forgot.
yeah.
I have some news to share with you. Manish has decided to leave Acronics and pursue another opportunity. So, yeah.
Okay.
I know.
So
I don't know if we should be hearing this.
okay, I know.
Yeah,
Okay,
he's
anyway,
going
so-
into
We should be
a
hearing
software
it for sure.
position, someplace he feels.
Yeah,
like
hang on. I
Yeah.
okay. I don't know of any way to.
they're also letting him.
Yeah. Yeah,
hybrid.
probably
Server's
if
host,
we
I
all
think,
talk,
can
we are
mute
gonna
him.
mute
He
Nick,
wants to be with-
so
closer to
that
his family
we,
for a
we
while.
don't hear.
For a couple of
You
seconds.
need like the
Okay,
kind of
who's
like
host?
the host.
Yeah.
So I would like you to pick up the bamboo fully.
I think
Are you fine with
whoever
that?
is host, if you click on the upper right of his
Okay.
picture, there should be. an
Yeah, and
option
then
to mute.
I'm having
I
Scott
think
pick up
that
the
host
last
has to do it.
engagement because there's a board development that may be coming down there. So he's well versed in that. And
Well,
then
I will
I'm going to pick up the big cat. And
try to keep going.
the entrance right now.
If
And
you
then
can, if
Oh,
you
as
can,
Alex,
those things
just
come along,
wait.
we'll figure it out.
Okay.
And,
But if you're
so
the
that's
organizer, click on the three dots.
yeah, we're working.
It's a long story. Hang on. I got to log back
Well,
in with
yeah,
the
yes,
account.
he
Give
still
me
has
1
to
second. I'm logged in.
communicate that, so
Never mind. None of
At
us have
this point-
admin control. I got to log out and log back in.
work inside the team. So I'm going to be sending out a note.
Sorry, everybody.
Oh
Maybe we exit the meeting, all of us, and then.
I know. So I know it's going to be a little.
Or someone
But he
has
kind
his
of-
phone number and call him directly.
Yeah, if we all exit,
And,
it's what's gonna happen
we'll see what happens with
is that
that.
Nick is going to hold the line.
with the
He's
rules.
gonna hold the
Oh,
meeting open.
okay. Won't help, huh?
A
Yeah.
meeting. Yeah. It's a meeting.
Okay. Enjoy your puja.
I kind of feel bad listening to this, so yeah.
All right. Well, okay. I'll start going now. Hopefully everyone can hear. All right.
Yeah.
So yeah, basically once you click on that link, it'll take you here. As far as immediately getting started, if you just click on the README, it basically talks about the kind of general usage. If you copy paste this line, it'll run the baseline version of the code. So this basically just says load and test the design. It gives you basically
Hey, Alex.
Yes.
1 second. I'm just going to mute you to see if I have mute control. All right.
It worked.
It worked. All right. Sorry about that.
Right. Awesome. Okay. So yes. So here. So basically, yes, you define or you basically pass the kind of library definition files here, and you could of course create your own or just add on to the ones kind of the examples which are provided, and then basically you pass a netlist and a system definition file here. So this is basically, this has a very small amount of information here. But then if you go into something, for example, if you want to modify the IO definitions file here, so this is an XML, there's this README at the beginning here, which kind of describes the format and what each of the components means in terms of defining different types of IOs here. So yes, so that's, if you want to get started, just download it, open the README. I think one caveat, which I didn't mention everywhere here, yeah, you have to use Python 3 here. It will not work with Python 2, so just make sure you're using Python 3, and then it should be okay. Yeah. And if anyone wants to do kind of more thorough modifications of this or editing of the model, I'm working on kind of more detailed, kind of thorough documentation in terms of kind of like a, I don't know, I guess a manual and something that goes through the kind of all the stuff you had in the PowerPoint here, and kind of connects that to the code. So I'm working on some of that right now, and that will be in a future version which is released.
Great, thanks for that overview. That's really I like the modularity of it and being able to like ultimately tie in, say, different processes, different chiplets, and just then in the end defining what you're trying to put together and then getting cost modeled that way.
Yeah, and I think something I think you mentioned earlier was that the big thing which we do want to add is to make it even more modular is this ability to black box. And if, for example, you're designing a chiplet where you're designing 2 chiplets and you're buying one of them, you can completely black box that chiplet, or you could bypass any number of parameters. So that's another thing which should be in a future release as well.
Does anyone else have questions for Alex?
I'm just zipping around muting people who aren't speaking. You will have to unmute
Okay.
yourself.
Okay.
All right, yeah. If there are any questions about, I guess, either anything specific about the code here, I could also go back to the PowerPoint and talk about one of the other factors.
So the one
yeah.
quibble I have, for lack of a better word, is much like Professor Iyer, I think your model is biased towards advanced packaging.
I'm sorry, you said it needs the packaging, you're saying, or what?
No, so Bapi, I understand your concern, but I think part of it, maybe you can help us with this, right? If you can give us some insight or inputs into the cost of organic.
Yeah.
That would help a lot. I mean, we actually desperately want to do that comparison as faithfully as we can.
Yeah.
So, Bapi, what makes you say that it's biased? I mean, I'm sorry, I didn't get the beginning part of the meeting. I joined a little later, but what makes you say that?
Well, it's UCLA. I mean,
Oh,
there's
that's
that.
right. Okay, all right. You just took that as
No, there's more. There's more. I 2 things. I think if I want to get nerdy, I buy the, hey, you got basic pad cost in organic, and that hurts on laminate. But the part somehow and maybe I had to go back and listen carefully, but it felt like we're undercounting the complexity of advanced packaging, in that they were counting the incremental cost of advanced packaging versus the startup cost of alignment and complexity was undercounted, is my first reaction.
No, so I mean, advanced packaging, I mean, the entire yield model for assembly is actually geared towards some advanced packaging.
Right, but there is, you've got a sort of X square cost, like 16 die, aligning 16 die in advanced packaging is probably more than quadratically expensive than aligning 4 die in advanced packaging, so to speak.
Yeah, so that is factored in the alignment yield, right? That is, it will be super linear, absolutely. So that alignment yield is chances of failure per yield, and it gets
I'm talking about the base cost as well, the actual cost.
Yeah, so the cost, I guess, for that would be, I mean, yeah, there's some, I guess, alignment costs. There's some assembly costs, and there's some yield.
Yes, exactly. So the complexity yield, the cost complexity going from left to right, incremental baseline cost complexity going from left to right in advance has to be higher than for laminate.
Yes, it will be higher
for
than
the
for
organic
laminate,
than for the laminate.
But I think that will factor in because you will put in alignment yield numbers which are going to be much higher for laminate than for advanced packaging. right?
Puneet,
Because if you're
so
trying to align to like a 100 micron pitch versus like a 40 micron pitch, of course the yield is going to be higher, hopefully, for the 100 micron pitch case.
okay, there are two things, right? Or there are three pieces, right? There's the raw cost of making this. There is the yielded cost, and you're sort of, in my mind, you're smuggling the raw cost into the yielded cost, if that makes sense. The baseline raw cost also goes up. It's not just that the yield goes down.
So when you mean by raw cost, is it the substrate materials? Is it
Just the cost complexity of aligning 16 die on aligning 16 die on an interposer, from what I understand. I don't have hard data, but
so the cost for that would come in.
I agree with
terms of,
Bapi. That's as you add more chiplets, you're going to be charged more.
No, absolutely. So I think, but that is that's the part I'm getting confused about. Why do you feel that that is not being properly modeled? Because
so to mention really quick here, so we do have basically we calculate the amount of time spent basically on each of these machines. So if you go from aligning one die to aligning 16 die, your time spent on the machine will go up by roughly a factor of 16. And that will add assembly costs, in addition to the fact that it's also going to hurt your yield pretty dramatically, because you're now going to be aligning 16 dies. So I guess dramatically, it depends on what your base yield is. We have some pretty high alignment yield. But basically, it will hurt your yield because that's going to be going up. That's going to be exponential if you're now aligning 16 dies.
I think,
Puneet, to answer your question, why do I feel that? And you're right, it's not like it's more that the curves look too far apart in that second last slide.
So I think, Alex, I think one part which we might want to redo for organic, especially, I don't know, what did you assume at the machine cost for organic bonders?
Yeah, that is certainly. Let me double check.
Because if you assumed it to be the same as the silicon bonders, that's being unfair to the organic. Because if you're going to do just solder reflow, I mean, those are significantly cheaper machines than a hybrid bonder, thermal compression bonding tool.
Yes. So let me check what actually made it into this run here. But yeah, basically the machine cost. Let's see. Yeah, so it's a factor of 5 larger. The bonding, so I'm assuming in this case, I was assuming the bonding and pick and place machine are the same. So I use the same parameters for both. But I assumed a $200,000 organic machine and a $1 million silicon machine.
No, so my quibble, I mean, I it's a quibble, really, not even it's more that in my head, as the number of die increase, the advanced curve should bend upward much more sharply. I think that's what I'm reacting to.
Okay, so
it kind of flattens out.
The silicon here should bend up more sharply.
Yeah, that's if with the right coefficient, at least that. I mean, Alex, that's what I'm reacting to.
Are you amortizing any of the NRE cost, design costs that are involved in the silicon interposer?
Yes. So I do. So okay. The thing is, I don't have good numbers for those. Those are modeled. You could put those in if you use the model. But since we don't have great numbers right now, they're set to basically don't care values.
Just from a industry's perspective, they're significant.
Yes, they are definitely significant. Basically, our plan on this is right now it's modeled. There's basically a mask cost, there's a design cost, and there's a quantity used. So if everything you are doing can be modeled there, you can add that in. You can basically use it with the current model, but we are planning to do a somewhat more in-depth handling of it, and then we'll focus on that.
Alex, just to answer this, even Bapi's quibble, maybe you can show the other plots that you have, which shows the silicon cost for much more fine-grained and much larger number of chiplets as well.
Okay, give me 1 second. Let me pull that up.
I think.
Let's see.
So while Alex is bringing up that, I have a comment about as you increase the number of chiplets, the number of die that you realize the functionality across. I think this was brought up a little bit about the off package or off system bandwidth starts to become an issue unless you incorporate long reach IO into the base die. You're going to have to put a IO chiplet on the periphery is how I would look at it. Of course, I work for a company which makes IO chiplets, so I would say that. But wouldn't that make sense?
No, yes, that is true.
That is true, but I think in the cost modeling sense, that is left to person who defines the system definition.
But the cost of the die is going to be impacted by whether you put these high-powered SerDes or not.
Absolutely. So, but there are two parts to that cost, right? The one is, again, was previously mentioned, the design NRE cost, and the other is kind of the wafer recurring cost. And the recurring cost can be modeled here right now, because that's just that SerDes area will be larger, it'll take up some space, it'll take up some power, and that is modeled here. The design complexity or the design NRE cost is what is it. We can model it. It's just that since the numbers are like any reasonable number is very difficult to come by, and it's so case dependent. That's why right now it's not. I mean, those numbers are too low right now, and they don't matter in these current results.
Okay, yeah, I mean, it depends on the bandwidth.
Depends on the bandwidth. It depends on how many lanes. It depends on what. I mean, yeah. So the high speed SerDes So they can be all modeled. It's just that the results that are generated are assuming they're ignoring it.
Okay.
So I don't know if this helps answer some of the questions. So these plots are a bit extended. So in the past slide, basically I'd limited to showing four chiplet version, 9 chiplet version, and a 16 chiplet version. This goes basically up at perfect squares all the way to 81 chiplet version. So that would be 9 by 9. So yeah, you can see a bit more here. On the left, this is basically the same kind of cost against number of chiplets. On the right here, it is cost against chiplet sizes, but they're the same numbers, just presented in a different way. And I guess the kind of main noticeable thing is here you see basically the organic parallel version, which is this orange plot, getting penalized quite dramatically as the bandwidth is increased. That's the most dramatic thing you see here. But yeah, this does kind of show a crossover point as well between the silicon and the organic, which you get later on.
Yes, I think in all these cases, the part I think what you were mentioning is there's a very significant penalty to kind of reducing the chiplet size too much.
Yes. And again, the consequent cost, and so it'll be greater than linear, basically.
Oh yeah, absolutely greater than linear.
So if the number of chiplets is increasing as square, and the cost is greater than linear, the cost will be greater than square, basically.
Yeah. So, and you can roughly see that. I don't know how much of it is obvious in these plots, but then it starts to matter a lot more roughly below the 40 millimeter square chiplet size mark. Because if that's where somewhere below 100 is where the chiplet yield basically flattens out. So you don't really get yield benefits of breaking the chiplets into further smaller little chiplets, but your assembly cost keeps on going up. So that's why even our previous paper, the argument it tried to make is if you're building high volume parts, then a chiplet size in the neighborhood of 30 to 40 millimeter square is probably the smallest you want to go.
Well, but look, if in the bottom left graph, right? you got some kind of a crossover between organic and which is also sort of how you know at an extraordinarily large number of chiplets you got a crossover of some kind. And assuming at large number of chiplets, there's going to be a minimum. I mean, essentially, when you increase the number of chiplets, the size of each chiplet stays a constant because you're sort of taking the same area and partitioning it finer and finer, correct?
The size of each chiplet doesn't remain constant. Size of each chiplet becomes smaller and smaller.
Smaller. I'm sorry. The overall die area is a constant, and you're partitioning it into smaller and smaller chunks.
It's not constant because you have IO cells, and also your integration substrate is getting larger because of die separation. So as you make it smaller, total area is going up.
Right, but at some point, when you make smaller chiplets, the IO bandwidth going into the smaller chiplet goes down in your pictures, right? So if you sort of
yes, but the IO, I guess the IO's per unit area goes up.
IO per unit area goes up.
So basically, if you decrease the size, if you go from this 800 millimeter squared to say the 200 millimeter squared version, yes, each chiplet here now has 16 gigabit per second instead of 32 gigabit per second on the monolithic. But that 16 gigabit per second is on a quarter of the area.
But half of that 16 is on or die-to-die IO versus off-package IO.
Yes. So I guess if you look in the kind of sensor, yes. But yeah.
And so now if I go to the finer picture on the right, I'm down to 2 gig. And if I partition it to 32, or excuse me, how much of the next one be 64?
Yeah.
I'll be down to 1 gig, basically.
Yes. So the amount per unit area is going up on the internal side. The external is staying the same.
Wait, why is the amount per unit area? Unless you're saying it's pad limited, so I'm just going to settle to a constant area for the die?
Well, so this does end up becoming pad limited at a point, which is where this kind of becomes a problem. So pad limited, and there's some consideration of IO cells, but I believe in this case actually the pad limiting is more of an explanation of what we're seeing.
No, so but I think Bapi, just to answer your question, if you look at the same picture, on the middle picture, the square in the middle picture is divided into 4 squares in the rightmost picture, right?
Yes.
And so in the middle picture, the square, there are 16 gigabit per second going out.
Right.
The bigger square. In the last picture, there is 8 gigabit per second going out of the smaller square.
Right. No, so so the part I'm having trouble reconciling is if you go to smaller chiplets and then laminate your pad limited because you're assuming 130 micron bumps, how in that graph are you getting a crossover from laminate to advanced on the for a large number of chiplets? How are you seeing a crossover when you basically in the bottom left graph at 64 chiplets, your chiplet size should be constant because of its pad limited? Why is the cost curve bending down for organic?
So I think, let me see. So first off, let me see, that's the version with the parallel IOs, which was the cheapest version before. So I think that it might be a matter of all of them becoming pad limited to an extent.
I see.
Yeah.
You see what I'm saying, right? At around 64
Yeah, I do see what you're saying.
Yeah.
Mm-hmm.
No, but if you look at it, the crossover is not between the parallel IO organic and parallel IO silicon. The parallel IO silicon is still way lower. The crossover is between parallel IO organic and I'm trying to figure out which one is that. That's
Yeah, this is
UCIe standard silicon. So they are the UCIe standard silicon looks. I mean, its trade-offs are very different.
No, the orange line is organic, right?
The orange line is
organic
organic. Orange dotted line is organic, and if you look at the thing that it is crossing over is the solid light blue line.
Oh, it's a solid, and that's UCI. Oh, wait, what is the difference between you?
But yeah, what is the difference between UCIe
Yeah.
standard
Okay, now Anu
versus
So UCIe standard
orange?
and advanced, they're basically two different, I guess in the protocol definition, there's basically one which is meant to be used on kind of more organic substrates and one that is meant to be used on advanced substrates.
No,
So
no, I'm
basically the
asking
difference.
the orange line. It says organic 5 nanometer, 100 volt CDM 2 millimeter 400. So how's that different from UCIe standard?
So basically that is a parallel IO cell definition. So here, this wasn't the one I cleaned up, but this is basically a parallel IO, which basically is defined in more of an AIB style. So basically there's more parallel wires which runs slower.
Alex, do you remember what was the per wire bandwidth in the parallel
IO? Let me check.
I think
But Bapi, if these two are intersecting each other, then it's really just that the parallel IO probably is smaller than the UCIe standard.
Well, the parallel IO.
Yeah, but they should
transceiver
all be
base-
pad limited. There should be any difference at all.
No,
2
parallel
gigabit
IO.
per second. So 2 gigabit per second per wire on the parallel style IO.
And so then it's going to have more pads than UCIe. So the crossover is still pretty confusing then.
The UCIe is at 4 gigabits per second. Is that what it is?
I'm sorry, what did you say?
Is the UCIe at 4, running at 4 gigabits per second, or is that 2?
UCIe, so the UCIe standard, so I'm assuming kind of the max rate which it can run at. So that means for standard, it is for 44 wires, there is 1024 gigabit per second, but that is a single channel. For advanced, so that is the bidirectional bandwidth. So that is half of that in each direction. And then the advanced is there's 4 times as many signaling wires, and about 4 times the bandwidth.
Okay, I apologize, Alex. This kind of stuff is really hard to do with many people breathing down your neck on a bridge. I'm sorry.
Yeah, no.
Yeah, no problem.
We've got to look at it a little closer, I think, but appreciate it really.
No, so UCIe, the UCIe definitions are based on the standard definition. It's not defined per wire; it's defined as a large IO cell, which because the standard gives the definition of the precise size and all the way down to the bump map. So there it's just taken. This is the size of the large IO cell, which is some millimeter by some millimeter, and this is the total bandwidth pushed out of it. In the pure parallel IO, the IO cell is much simpler and much smaller. It's basically a cascaded buffer with small amount of ESD protection.
And one other thing to note here, I guess, is if we're getting to the point where, for example, for a very large number of wires here, and if we're getting to the point, or for a large number of chiplets, where basically the bandwidth is much smaller than the max possible for the UCIe, the minimum number of UCIe connections they can have between those two chiplets is 1. So that means there is going to be some rather poor scaling there. So it's possible, I guess, what we're seeing here, we're seeing the parallel kind of tip back down, and the organic, it's possible that one is just basically purely down to every connection has a single UCIe. So every time you split again, there's just flat linear, or not linear, but I guess quadratic in this case. There's scaling, or linear with the number of chiplets, but there's just scaling of the area. Whereas the the parallel is kind of moving back down to be below that again, because it's much more finely separated.
I just wanted to add that if you model it with fewer parallel wires, right? So there are people who have proposed, not going up to, going less than 16 bits, right? So, which is the standard, and then your graph would look dramatically different, right? So let's say if you said the minimum now was 4 or 8 in each direction, I think that you would have a dramatic difference on those as well. I just want to make that comment.
Yeah, that's quite possible. Yeah.
I would have one other question, kind of like underlying question to all of this. So we're talking about like splitting up these die or like the system into smaller chiplets, and then accounting for what is the phi size and how that scales basically the area. The way that you're building your model, like you talked initially about kind of the chiplet definition, where you talk about like where you basically say how large the area of the die is. But then does the model basically dynamically scale the actual area of the chiplet to account for smaller or larger I/O needed when breaking it up, or was that you going into the definition itself?
So okay, so the way I did this, the way I generated this is effectively I wrote a script which is not actually included. If you want to rerun this, I can actually provide the script I used to run this. It's not in the.
No, Alex, I think the question is slightly different. Question is saying that when you change the IO type, do you adjust the chiplet sizes within the code, or you're expecting somebody else to specify it?
So when I change the IO size,
IO style, let's say I keep the system definition.
That's handled dynamically.
Yeah.
That is handled dynamically. The number of IOs which are defined and the number of connections, like the netlist file, is regenerated each time. However, the areas basically
for example,
calculated based on the number required for the bandwidth.
Alex, for example, if you keep all the bandwidths the same, the system architecture the same, etc., and all I want to do is make all these IOs go from I don't know, UCIe standard to parallel, and make no other change, then in your configuration files is the only place I'm supposed to touch is the netlist definition, which says changes the IO type from let's say UCIe to the parallel version, right? And everything else will get adjusted automatically.
Yes, that's where you need to change it. Yeah, just then go into the netlist file and for a connection, swap the UCIe standard for advanced. If you make that change there, that would change that connection.
Right, but then does that basically change? Does that change the silicon price? Like assuming that you now have a smaller die because you have a smaller phi, it would do that. So to that degree, the effective chiplet size is basically what you put in as say the logic or RF content, and then it adds to that whatever you define as IO.
Yes. So basically, there's 3. To jump back to a previous slide I had. There's kind of 3 things which could limit, sorry, not this slide. There's 3 things which can limit the area. So basically you can either have, which is core plus IO cell. So that is basically, I guess, silicon area, or it could be determined by, I guess, stacked dies, or it could be determined by pads. So those are the kind of 3 options which are handled here. And that's kind of handled dynamically.
I see. Okay, that makes sense. Because in that case, just one other comment I was thinking about during the talk, like there could be other like infrastructure type elements that you need to put on a chip when you're separating it into 2. And like, I guess that's more advanced and depends on whoever wants to implement something, and they'll know, like, for example, they need more like a clock on each chiplet when before it was 1 clock, now it's 2. And but anyway, basically being able to account the dynamic scaling of chiplet area based on how often you partition it.
Yeah, so if you're doing a design, so I guess what this is well suited for is if you have a couple of configurations and you kind of know the general core area for each. Yes, there are things like, I don't know, network sizes or networks which would change. There's a few different things that do not split and would need to be included on each, like short clocks, possibly voltage regulation. There's a few different things. Automatically, we handle the IO cells. The others would have to be manual, and you'd have to include that in the core area for your block definition.
Gotcha. Okay, that makes sense.
So the graphs that you generated are was kind of specific to this graph processor example.
Yeah.
Is that right? And
that is correct.
Yeah, so obviously, if you had like memory and stuff like that, memory interfaces and stuff like that on, the inside chiplets are going to be starved for bandwidth in some ways if there are memories around. So it is not necessarily representative of other types of scenarios, I guess.
Sure, that's correct. Yeah, I mean, some similar scaling trends you could probably apply, but yes, you'd have to do a different analysis there.
Any other questions for Alex? I think we've had a very good discussion so far. All right, so then I guess I would have a couple other things to talk about our white paper, but first of all, Alex and Puneet, thanks a lot for joining and taking so much time. I mean, this was over an hour and a half, but I hope that the feedback from the group was helpful to you, and I can also follow up afterwards by email and see if there are any other public data that I'm aware of, like the kinds of things that you requested during the talk to just make your models more accurate.
Yeah, that would be great. Yeah, thank you.
Sure. Thanks for joining.
Thanks a lot, Mark. Bye.
All right.
Bye.
Bye-bye.
Bye.
Okay, so I just want to talk a little bit more about the white paper we've been working on. I know there was a break last week, so it's been a while. I think in terms of, I've been adding a couple more components here. Let me share my screen also to show where we are. Okay. Oh, Trent was saying that he was having to leave. Okay. Let's see. Oh, there's a lot of buttons here now.
Marek, you're a co-host now.
Yes, awesome. Okay, I was going to say I could see so many more things going on here, like the AI companion and so on. Okay, let me take screen 3. So thank you, Rajesh, for adding adding more to the test section, which I'm going to jump to. That's here. So I haven't had it, like I've just skimmed through it, but I appreciate the drawing that you put in here. I think that makes it a lot clearer. And then also that you put in, instead of having these bullets, like having more kind of like written text to walk through like what each of these sections are. Do you want to like comment on kind of what you were thinking, like going through this?
But I did the same thing when I generated that first part.
Yeah, so I think I mostly simplified the flow for our discussion, I think 3 weeks ago before I went for vacation. So that actually just wanted to make sure that it is seen as a totally business side instead of going into too much technical. So I just removed and make it easy. Can you hear me?
Oh, yeah, we can hear you. Thanks. Yeah, no, that makes sense.
And actually also added the pictures. I think the picture are worth. So instead of putting it all these cost components coming from all the way from wafer all the way to dissecting and packaging and putting it on a package, I just put some factors there in one package because there will be pre-assembly test and then post-assembly testing. That's why I think I missed one of the arrow from that package all the way to these 2 components. I could not add that, but that's fine. So there's an arrow from the final module level test to what isolation and repair, and then yield learning. Yeah, these are the 2 outputs. So that's basically comprises of how we can model their test cost.
Okay. One question I had here was, so there is wafer level substrate test. and you're showing this here as a circle. Do you mean this is the substrates when they're still, say, in a strip, or are you talking about like reconstituted wafers, or like why is the wafer level and substrate combined in one test?
We assume that there'll be some substrates that can be commented from our substrate folks. However, the substrate manufacturer are their big wafers, and then they are put into a size of the wafers substrate that comes out of the silicon.
So are you saying basically whether in the substrate manufacturing process, whether at any point they are put into a wafer-like format and then probed at the wafer level?
Yeah.
I see. Okay. I mean, I guess like Trent dropped off, so we lost our like most definitive expert on this. But my understanding was that at least packages, like depending on like the type, I guess if you have silicon, like if you have an interposer, then you would have just an interposer, like then that would be silicon. But if you're talking about organic substrates, you would have like more rectangular shaped.
Like, actually that's rectangular shape for, I think, as shown in the right side, but I think that we can finalize if that shape is that matters from the figure, but we can talk about that, because that needs to be, that information will come from actually wafer level, how the substrates are manufactured at the wafer level.
I see. Okay, so you're talking mostly then about, let's say, silicon interposers.
Yeah, that we need to. If you want to generalize it, then we can change the figure.
Yeah, I think it may, like, if we want to just have a generic like image that like portrays chiplets on, and I know that things would slightly change depending on whether you have chiplets that sit on a silicon interposer and then on a substrate, or silicons that are fan out molded and then go on a substrate, or silicon or chiplets that directly go on a substrate. But either way, I feel like in this case, at least that was the one thing when I was reading substrate test, but then saw that it was round, I was confused as to what that substrate looks like. And if we keep it more generic, then maybe that would make it applicable to, like I think if you look at all of the semiconductor products, like organic packages, like, or just a fraction of it is silicon interposer, and a lot of the other stuff is not. So then I would want to make sure that we're also including that, or not suggesting that everything is silicon interposer based.
Okay, we can make it tailored to that interposer. Because I think interposer which does go on the top of the substrate, right?
Yes, exactly. That would then still go on top of the substrate. Yeah.
Right.
Gotcha. Okay. Any other thoughts from anybody? I'm not sure who has had. I think Rajesh added this just last night, so I'm not sure if anybody has been able to take a look at this yet.
Yeah. So basically, I'm dissecting the test cost into substrate cost versus the chip level and then package assembly test cost.
Okay.
Sorry, my voice is breaking because I have a lot of cold, because I just came from India last night.
Oh no, I'm sorry to hear that. Yeah, I hear you having a little, or like sniffling a little bit. Okay. I hope you feel better soon.
Yeah, no worries.
Okay, so then
does this also include some kind of capex costs for the probe cards and stuff? If we need special,
that's a good point. No, it does not. Right now, actually, if you look into this, that ATE, actually AT timing and all that stuff, it's not included here, because even
I see. Okay.
If you take at the law, that's why I actually put that figure on the top, because if you take out the regular flow, it should be only the last substrate and bare die. It should be the flow, but I added the two top blocks because that's the way where we'll be thinking from the top level test issues. Because when there is a global supply manager is for any chiplet level person is responsible for product, and you'll have to take care of all these what
see.
test patterns, what test costs. I mean, he has to start analyzing right from the top level, tester platform selection and all that stuff. So that kind of, I think we can add that comment. That's a good point.
Okay. So in the the original cost model that we had created many years ago, we had this one I think a flow chart where we talked about the test cost at a high level, and it was really very high level.
Okay.
It included probe costs. Of course, we didn't take CapEx. We had a separate column in our cost model for NRE. And that would kind of include some of the CapEx items, which are, one-time payable, expenses for cards or expenses for masks, which are again NRE fees. So we had probe costs. And then in that we allowed, we would put in how much time it takes and the cost, loaded cost per hour for probing. And then we had package level test, which again we represented as either a single insert or a double insert. And for each insert, how many seconds and the loaded cost of package level test. And then the third one we had was system level test, which probably may or may not happen everywhere. But in certain cases, if you're doing a system level test, then there would be the loaded cost of putting your SIP in the environment that it's going to find itself and do the testing. So those were the broad three pieces. Yeah. Hey, who produced that? Good job, Marek.
Thanks. I just just pulled it up.
Yeah, so this was kind of what we had looked at as the three pieces that go towards the total cost. When you talk about substrate testing cost, we're talking about, does that fall into the packaged or module cost? Because that's when you're actually testing, the ball to, from the signal from ball to transporting it around the chip. Or am I missing something? Are we missing some piece here?
Like in the beginning, the substrate test is for probing, like rank probe. I'm talking about that to check the integrity. Okay. Like that also will be cost because a lot of machines, they have probing machines like a single probe or double probe test to check the continuity. Right?
I see. Okay, got it.
Yeah, and if you are in a production flow, substrates get tested separately and you're using a machine, then you'll be using a sort of a traveling salesman problem to optimize the test cost, because you're basically visiting a lot of interconnects on the substrate and make every net is tested at least once. So that kind of stuff. So that is before assembly. And then you, of course, after module is built, I mean, assembly is done, then of course that substrate will be, all this interconnection will be tested through either JTAG through 1838 or interconnect test.
Okay.
And you're right, multi-site test also is another component. I might have added that in that figure, that when we decide you're going to do package level test, either single site or multi-site test will be there. Because in that second bullet, which is ISS system and the peak is design engineering, the output is called assembly, and also we need to talk about the load board. I can add that.
Okay, I mean, I think at least like single versus multi-site testing to me sounds more like it's like detailed information. Like ultimately, this comes down to how like in the cost counting, but you can always model that by saying your machine cost is going to be, say, a quarter of like another product, because you can test 4 products at once, or you put it into the timing factor and say you can test it in the quarter of the time because you're doing 4 in parallel or something like that. So I wouldn't necessarily like put in all of that detail in the graph if we just want to get the basic message across of how do you have to think about test cost contributing towards chiplet designs.
Understood. That is fine. But I think Anu made a point, last point, third point was actually is very important, like system level. We used to call it SLT, system level test.
Yeah.
And that actually is more costly because clock is running very slowly, like in kilohertz. And sometimes it is required. So we want to put that in the figure.
So
on the right
I
side.
guess so when you say module level test here, that is not the full system yet then, like, or like that's a question, because it looks to me like the module level test could be, it looks like the last step here, so I could consider that being a system level test.
That's again, yeah, it depends on what we because this finally all these final chiplet is going into a big system. Then when I'm talking considering system level test means basically you are in a big board or machine where you are running operating system. Maybe
Right.
that is too much.
I mean, I would stop the testing at like, my understanding was that system level test is still, you have a packaged part that has a lot of die on the inside, and the test environment now is the rest of the system that part would sit in, but it's still basically it's still like an additional, like basically a fancy final test version where you just, yeah, okay.
So actually it depends on application, I mean scenario, but what you are saying is right. That's what also system level, basically the product goes into the actual final end use system, and it may be using either a JTAG or dongle or sending a service processor transactions to test the entire system in the chiplet in the system. Yeah. So that is more costly, and actually I don't know whether that needs to be reflected here.
Yeah, I mean, I think we should at least like put in somewhere like where it makes sense within the graphic to say that there is also like an optional system level test, and that the cost of that obviously people would have to figure out with their respective test departments.
Yeah, we can add that in a sort of a verbal section instead of in a figure.
Okay.
And you want me to take the table below out? I can, because I think you had a question on the comment that I just wanted to summarize, but we can put it in the appendix if you.
I think just given kind of like space constraints, and like now we're more at like 3 pages, I think it would be better to probably move that to the appendix.
Yeah. That is fine.
Okay, awesome. Kash, do you have anything on the open market section? I think there are still some comments. Like, have you any chance to go through that?
I haven't had a chance. I apologize. I'll try and look at it this weekend. I know I've gotten kind of busy or busier.
Yeah.
So I haven't looked at any of this. So yeah, I'll try and look at it this weekend.
Okay.
Apologies. So
no problem. Right. Okay, thanks. I think otherwise, like aside from Kash's section where he would need to look it over one more time, and we talked about the test one, I think all the other sections look pretty good. So I would also ask people to, like, at this point, like basically go through the entire document and just give comments, because to me, otherwise it looks pretty reasonable, and I just want to make sure that everyone knows all the aspects that are in the white paper, and before we say, okay, this everyone agrees with the content in it. So is that, like, I know that that's in total, like at least the main text, like 20 pages to go through, but what do people think, like is, say, in 1 or 2 weeks to have comments from everybody, or at least kind of a sign off saying, like, yes, I looked through it and looks good to me, like even looking for typos and things like that?
Yeah, I think it's a good idea, and you have to put a deadline on this, right? So
yeah,
I get it. So we all need to sort of knuckle down a little bit,
Yeah,
especially me, and just get it done.
Sounds good. Okay. So then, like, I'm not sure how busy it would be great to have this all like certainly like flushed out before Thanksgiving, because I think after that it's basically the end of the year and then everybody's in holiday mode anyway. But so let's say if like let's hope that Kash has his edits in within a week, let's say. So I would say it's reasonable to also say in 2 weeks, so that would be the 10th of November to have everyone's feedback on the document, so that we can then by then say we have basically a final version that we then just need to go through kind of like editorial changes, such as making the like adjusting titles and things like that, but nothing like content wise anymore.
You mean that before Thanksgiving?
So this would be the 10th of November. Like by the 10th of November to have feedback from everybody, so that we can then like pull all of that together. But by that time, everyone has looked at all 20 pages of the main document.
Okay, that's before 1 week before Thanksgiving Day. Okay.
Yeah, exactly. So that would be before and then we would have like say another week or two to actually do the edits. But I think it would be good to I'm not sure, like it took me about like 2 hours maybe to read, or an hour and a half to read through everything and give comments where necessary. So it's basically asking for that.
Right.
Okay. That sounds good. So then I'll send a kind of reminder email to everyone who I also added kind of like all the authors here in the document, and I added an abstract. And so I'll email all the authors to say basically this is by when I would like to get this done, and then people can do this on their own time.
Sounds good.
All right, awesome. So I know we're already at the end of our business meeting. We had a lot of discussion with the cost model, but I think that was very insightful, and glad to see that that's all open source as well. So yeah, then let's just meet next week again and see where things stand at that point.
So Marek, I have a question.
Yes.
So the cost model presentation was announced. It was to be start today at 8 o'clock. You guys, I missed the beginning.
Oh yes, yeah. So I guess I'll send out the link to both. Yeah, I think I mentioned this at the end of last time.
Oh, okay.
They Boppy had also expressed interest, because this would be a topic not just for the business group but for everybody. So yes, that started at 8.
Is it recorded?
It's recorded, so I'll send you
good.
the link to that, and I guess I'll reach out to
Thank you.
Praneet and Alex if they can send us the slides as well, so that people have access to that too.
Sounds good.
Yeah.
Yeah, if it's share that, I think if you get that, that'll be.
Yeah. No, I mean, I think it was very well thought out, and they went into a lot of detail about all of the aspects that you would need to consider.
One quick question I think I didn't get to ask. I'm not sure if you guys get it or not. I saw he has model for that machine there, like big amount. I assume his model is based on that if you want to build this everything by yourself, or I thought like not factoring like if you're going to use a foundry to use it, right? More kind of factor the foundry cost rather than. You see what I mean?
I think.
Sorry, Marek, would you mind ending the meeting when you're done? I have to leave.
Oh yeah, of course. No problem. I'll end it. Yeah.
Sorry, James. Right.
Yeah. No, all good. Yeah, no, that's a great question. I think this is kind of coming from their point of view, so they don't necessarily know from an OSAT how much is a reasonable cost per hour of a tool for, say, pick and place. So I think they approximated that cost by saying, we know we can find costs of a tool that does that job for, say, $200,000 or $1 million, and we assume such a tool would live for 5 years, and then break that cost down, and then they get an hourly cost to operate it, which obviously is not necessarily a correct approximation, giving maintenance and everything else that may happen, but it's a first step, and you can fill in the numbers yourself to get an hourly rate.
Right. Yeah, I think that probably may not be the most of the use cases, right? Given most of the companies, that may not be the case, right? No, that's a comment, but good. Thanks for that info.
Yeah, I mean, it was a great academic exercise, right?
Okay.
So I mean, I think other than that,
any other
it's a good
questions?
first step. Agree.
Yeah.
No, thanks.
Thank you, guys.
Okay.
Yeah, thanks.
Okay. Bye, everyone.
Bye.
Yeah,
Bye. Thanks.
Bye-bye.